Hey folks, in lesson 22, we're going to tackle two particle collisions. And what we're doing here is we're taking two particles that are going to hit each other no matter what, and they have a particular velocity per particle, per mass, and then the whole goal of this problem is to figure out what the velocities of these two particles or these objects are after they collide with each other. So our approach is going to apply what we know about impulse, what we know about momentum, and we'll also make some clever assumptions about geometry and energy loss to model this effect. And the reason why is because when objects collide, they deform. And we've dealt so far only with rigid bodies, and we're going to continue doing this. This is the only time in which we actually talk about deformation, but we're going to characterize that in terms of compression and then restitution, but we're not actually going to look at how much it compresses. To do that, we'd have to actually work through some finite element models and some really complex procedures like that. So let's get started, and let's talk about the different phases of a collision. And defining these phases is important because we need to be able to define different and distinct time points in which we do our analysis. So the first phase that we have is going to be an initial phase, which is before the collision occurs. And during this phase before the collision, the objects they have their own velocities, and they're coming toward each other. So they have a relative velocity that is closing in, that's aimed toward each other. So likewise, after the collision, we have another phase. And so this, after the collision phase, that's what we're solving for. We're solving to obtain the velocity of particle Q and the velocity of particle P after everything in the middle has happened. And so if we've got before the collision and then after the collision, then we have a during the collision. And so during the collision, this is where the impulse occurs. And so the impulse is the forces that are being placed upon Q by P and by particle P by Q. And so we can see that here's what this impulse looks like. Now we'll get into more details about that particular shape and about what we should expect about these impulses. But here you see the impulse on P by particle Q and the impulse on P by particle Q, and it looks like an impulse. Now if we look more closely at this impulse, then what we see is that at the very beginning of the impulse, which is the second diagram of impulse, then that's where our particles are just touching each other. And we're going to call the very beginning of this impulse T1. And then what's happening is the particles squish together, and so we call this phase the deformation phase. And then there's some point at which the particles are squished together as far as they can be. And so we'll call that point Tc for the time at which they're at max compression. And then from Tc to T2, T2 being at the end of when they're unsquishing, the unsquishing we call restitution. So the restitution phase. And then this is going to be the end. T2 is the end of the impulse. Now if we take a closer look at what's happening just during this impulse, is that from the beginning of the impulse, and they begin to deform, they begin to squish together, what's happening is that the relative velocity between the particles is going from its initial condition at T1 to its condition at Tc, which is 0. And so you see that expression here, where v of p with respect to q, as observed in the inertial reference frame, and then it's in the en direction, which we'll define in a moment, is equal to 0. And so the relative velocity is 0 at this point, and then during restitution, so it's losing relative velocity during deformation. And then during restitution, what's happening is we're now regaining that relative velocity in that en direction. And then the relative velocity that we gain during the restitution phase is less than the relative velocity that you lose during deformation. Let me say that again. The relative velocity that you gain during restitution is less than the relative velocity that you use during deformation. And that's if you have an elastic collision. And so we see this here in our impulse, because in our impulse, during deformation, we have a particular area, because remember, impulse is the integral of your force from T1 to Tc. So our deformation impulse has a large area, or larger area, than our restitution impulse, which goes from Tc to T2. And so what that means is that during the deformation and during the restitution is that we're actually losing energy in the system. And so we're going to discuss a way, after we deal with conservation of momentum, about how we deal with that energy loss. Now, in all of our dynamics problems, we always set up reference frames. And when we're dealing with collisions, we have a special reference frame. Of course, we set up our inertial reference frame, which is I is equal to typically O, and then we'll use E1, E2, and E3. And then what we'll do is we'll set up a collision reference frame. And this collision frame will be defined by the beginning of the impact through the end of the beginning of the impulse through the end of the impulse. And so this point here is going to be the exact same as at T1 as it is at T2, because remember what's happening during an impulse. One of our assumptions during an impulse is that the particles that are involved in the impulse don't change position, they only change velocity during, in this case, which would be the deformation impulse and the restitution impulse. So the point between the particles is going to be O prime. That's going to be the origin of the reference frame. And then the first unit vector that we'll define for our basis will be E sub n. And E sub n is defined as the velocity of p with respect to q at time 1 divided by the norm of the velocity p with respect to q at time 1, which is the magnitude. And so this is going to give us a unit vector, as you can see in this sketch, that's perpendicular to this plane of impact in between the particles. And so this is called the line of impact, and that's defined by En. And so this is slightly different than our path frame, so don't confuse this with the path frame, where we're defining our E sub n first, not our E sub t. And then our E sub t is then defined, this plane of contact is defined by crossing E sub 3 with E sub n. So whatever your E sub 3 vector is, basis vector, however you've defined that in your inertial frame, in this case it's defined as coming out of the page, then you're going to take the cross product E3 with En to gain the ET, and that being the tangential vector or the vector that defines what we call the plane of contact. So now with this reference frame, that gives us the tools to split the velocities, or split the velocity into different speeds, or speeds in the En direction and the ET direction, which we'll do in just a moment. Now, before we get to modeling these collision dynamics, we need to make some assumptions. And this is something that, as a good engineer, this is what you should do to be able to simplify our problems but still get good solutions. So we make some key assumptions. The first assumption is that the collision occurs over a short interval of time. That prevents us from having to model every single force in the deformation in between the particles, but to be able to capture them simply in an impulsive force, a single impulsive force. And it also allows us to use our assumptions that come with impulse and momentum. Where we apply an impulse, it changes the velocity of the particle itself. Our next assumption is that the objects are small particles. And this is perhaps the most unrealistic assumption that we have, because anytime we have anything colliding, they're not infinitesimally small particles, they're not a mass that's simply located at its center of mass, and they don't always collide in such a way that it makes a really nice plane of contact or plane of impact as well as a line of impact. And so this is probably our worst assumption, but regardless of this, you can still solve these problems and get very good answers of this. Our next assumption is that there are no external forces that act on either particle. And this is usually a pretty good assumption depending on what we're modeling, but what it does allow us to use is conservation of total linear momentum. Because recall that if there are no external forces, then linear momentum is conserved of the total system. Our final assumption is that there is no friction between the objects. And so that means that there are only forces along the line of impact. So forces along the line of impact. Now, this is a pretty good assumption, except for when we have the cases in which we've already dealt with, which is where you have a completely plastic collision, or what we call the completely sticky collision. And in that case, you have two objects that collide and then stick together. Because to stick together, you need to have friction forces, and because we don't have friction forces in this model, it's not the best for modeling that. You'll see we're going to have a one-dimensional case at the end of the lesson, in which it holds just fine. But anytime that we have what's called an oblique collision, which is what we see in this diagram here, then it's best if you have a sticky collision, that just go ahead and model it using the conservation of total linear momentum, as we've done before, instead of dealing with what's coming up, which is the coefficient of restitution. So let's start to capitalize on several of our assumptions. The first assumption that we're going to use is going to be that there are no external forces that act on either particle. This was our assumption number 3, and this allows us to use the conservation of total linear momentum, in which the time derivative of this total linear momentum is going to be equal to 0. And we've written this many times before, and so this expression looks like this, in which we have the mass of p multiplied times the velocity of p in the inertial reference frame at time 2, plus the mass of q multiplied times the velocity of q with respect to O in the inertial reference frame at time 2, is equal to the mass of p multiplied times the velocity of p in the as observed in the inertial reference frame at time 1, plus the mass of q multiplied times the velocity of q as observed in the inertial reference frame at time 2. So you've seen this before, we've done this multiple times, but we're interested in how the masses move relative to each other. Recall that in this collision, we have defined this point TC in which their relative velocities are 0. So let's take advantage of our collision frame, this new frame, and write out our total linear momentum in terms of speeds within each of those basis vectors. So during the collision, we'll model our speeds, or our velocities, as v, p with respect to O, so this will be the velocity of p in the inertial reference frame, as up, this will be the speed in the et direction, so just a generic time, so this is in the et direction, plus vp in the en direction. And recall that these directions, the e sub t is in the plane of contact, that's our tangential, and then our E sub n, which is along the line of impact. Let's draw a free body diagram of our collision, and in our collision we have particle P, we have a particle Q, and then we have these interactive forces. So this being this particle P, this particle Q, then this will be the impulse on P by particle Q, and this is in the, remember we've got our basis vectors, we have an E sub n in this direction, so this is going to be negative F Q P in the EN direction, and then likewise we have this impulse, need a hat on that, F Q P, and this is the magnitude F onto Q by particle P in the EN direction. So these are equal and opposite. This is going to have the same magnitude. And so FP onto Q, FQ onto P, these are the same magnitude, but opposite direction. So you see that we have a negative EN, which is in the negative EN direction for the impulse onto P from Q, and then in the positive EN direction with the impulse on Q as a result of P. So when we write our momentum using this expression of our velocity for particle P, and this is particle P only, not the total linear momentum, but we write our linear momentum expression for that single particle, then we get the mass of P, and this will be multiplied times the speed UP at time 2, and this is in the ET direction, plus the mass of P multiplied times VP at time 2. This is in the EN direction. That's our time 2. Now let's take care of time 1, which will be the mass of P multiplied times UP at time 1, and this is in the ET direction, and this is plus the mass of P multiplied times VP at time 1 in the EN direction. Now momentum of this particle, of this single particle P, is changing, and the reason why it's changing is due to this internal impulse onto P from Q, and we know what this is. So it's minus this magnitude F of Q comma P in the EN direction. And so we have our complete expression for the change in linear momentum of the particle P. And so we can write a similar expression for our particle Q, in which we use UQ in the ET direction, and then VQ in the EN direction. So this looks just the same as all for the mass P, except for this last expression, in which the impulse applied on Q from P is going to be in the positive EN direction. So we've done this before, in which because this is the force interacting between these two particles, then they're going to have equal and opposite sign due to Newton's third law. Alright, so let's stop for a moment and look at these two expressions. So the first thing we should notice, because we're in the collision frame now, in which we have the EN direction, and then we have an ET, E sub t direction, then what you should notice in each of these expressions is that we have a momentum expression in the ET direction at time 2 and at time 1, but notice that the impulse only occurs in the E sub n direction. So it only occurs along the line of impact. Now this is true for the expression for particle P. It's also true for the expression for particle Q. There is no impulse in the E sub t direction, or the tangential direction. So what this means is that speed in the tangential direction is completely unaffected by the collision. And so you can see that just by taking the E sub t terms out of our expression for our mass P, and we get MP UP at T2 is equal to MP times UP at time 1. Now because mass isn't changing, and these two are equal to each other, UP at T2 has to be equal to UP at T1. And we get the same result for our mass Q. And so this is a fantastic result, because it essentially means that the speed in the tangential direction, once we've defined our collision frame, stays the same and is really just very trivial. And more importantly, go back to our problem statement, which says that if we know the velocities at time 1, which is what we're assuming here, we know the velocities because that's what's given to us. We're trying to find the velocities at time 3 and then in that last phase in which they're separating. And if we know those velocities, that means that we know the speed in the tangential direction at time 1. So if we know these guys, then it's going to be the same at time 2 and after. So now that we've dealt with the tangential direction and essentially shown that it's trivial, then let's deal with the EN direction or the line of impact. And so with this, we're going to take our two equations in which we have our momentum for our particle P and our momentum for our particle Q, and we're just going to add them together. And when we do this, just like what we did in lesson 20, I believe it was, when we do this, then we see that our impulses just simply cancel out because they're in equal and opposite directions. And what we get from this in the EN direction is a conservation of momentum, of linear momentum, along the line of impact. And if we write that out, it looks like this, in which we have the mass of P multiplied times the speed of P. This is all within the line of impact at time 2. And this is at time 2 plus the mass of Q, the speed of Q along the line of impact at time 2 is equal to the mass of P, the speed of P at time 1, plus the mass of Q times the speed of Q at time 1. And so all this is along the line of impact, or we can say that's along the EN direction, whereas these expressions are in the E sub t direction, the tangential direction. And so in summary, what's happened here is that if we know the speeds of the masses at time 1, this is in the collision frame, but not at time 2, then we have 4 unknowns that we're dealing with. We need to figure out what U sub P at time 2 is, V sub P at time 2, and then U sub Q at time 2, and V sub Q at time 2. Now we've got 4 unknowns, and we've developed 3 equations to do this. We've got these in the tangential direction, which tend to be trivial, so we can mark off our U sub P and our U sub Q pretty quickly. But for our V sub P and our V sub Q, we only have one more equation to use. So we have 4 unknowns, we have 3 equations, and so with these 3 equations that we've taken from conservation of linear momentum, we still need one more. And so to get this, so far using our conservation of total linear momentum and linear momentum about each particle, we've used T1 and T2 for all of our expressions. So let's go deeper into the impulse, and let's pull in T1 to T sub C, and then TC, T sub C to T2, to understand more about how the relative velocities change with respect to each other during the collision. So to do this, let's go back to our collision. And during deformation, what we see is that during this deformation impulse, what's going to happen is the speed of the particle itself is going to change, or the momentum is going to change due to this impulse. And so we're going to write this out as this. Remember, we're dealing only with momentum. We're only dealing with the line of impact. And so that means we're going to have our mass P multiplied times our speed P at time of contact. So we're looking now from T1 to TC is equal to our momentum at T1, so MP VP at T1, and then we're going to apply that impulse, which we defined as negative F Q comma P, from T1 to TC. And this is where our impulse here is our deformation impulse. So the area under the curve from T1 to TC. Now we need to write out our expression for our change in momentum during our restitution impulse as a separate impulse momentum equation. And so for this will be MP VP, and now we're at time 2, and so we're starting at time C, so that's MP VP at time TC, and then this will be minus Q comma P, and that's from TC to time 2. And so this is our restitution impulse. Now, one thing we know about collisions is that during a collision we have energy that's absorbed in the collision. And what that means is that our kinetic energy is going to drop. So we don't get all of our speed back that we put into the system. And so what that says is that VP, let's say TC minus VP at T1 is going to be greater than VP T2 minus VP at TC. So essentially we're saying that the speed that we lose from T1 to TC, shown here on the left-hand side, is going to be greater than the speed that we get back during our restitution. So here's the speed that we lose, and then this is the speed that we get back. This is also called the rebound speed. So this is we're getting that back during restitution as a result of that impulse. And so the assumption that we make on this loss of energy is that we can simply make a ratio of our impulses. So Q comma P at T sub C to T sub 2, and divide this by FQP, and this is our magnitude, from T1 to TC. Okay, and so what that's saying here is that our momentum from ratio of our momentum from TC to T2 over T1 to TC. And so when we write out our momentum, it's MP, and then this is VP, still just dealing with the particle P, at T2 minus VP at TC, divided by that momentum expression, so MP VP at TC minus VP at T1. And so we get to cancel out our masses in this. And so because our impulses are equal and opposite, we can also write this out for the momentum, change in momentum of MQ. And so this would be negative MQ multiplied times VQ T2 minus VQ TC. Then divide this by negative MQ VQ TC minus VQ T1, and we get to cancel out our negative signs as well as our masses here. And it's this expression, this ratio of what ends up being these just changes in speed from TC to T2, or TC to T2, and then TC to T1 for each particle. This is our coefficient of restitution. And we designate this simply by an E. So let's do one more part in this to make this so that we can use it, and that's we're going to apply the condition V, our velocity of P with respect to Q, so this is our relative velocity between the particles, at time C in the along the line of impact is equal to 0. Remember, this was part of our definition here, in which we said at TC, at the max, it's squished together and it's at our max compression, the relative velocity between the particles is equal to 0. And when we do that and we rearrange some terms, then we get the expression in which our coefficient of restitution is V sub p at T2 minus V sub q at T2 divided by V sub q at T1 minus V sub p at T1. Alright, so now this is a workable form of what we call the coefficient of restitution. And so this is a ratio of speeds. So let's take a moment and let's analyze this. So our denominator, it's V sub q minus V sub p at both at T1. And so this is nothing more than our approach speed, which is the speed in which particle P is approaching particle Q. Because this is a relative speed because it's VQ minus VP. And remember, all this is occurring, this is in the EN direction. So this is along the line of impact. And then in the numerator, if we've got an approach speed in the denominator, our numerator is telling us VP minus VQ at T2. And so this is our separation speed. And so it's the separation speed because at time 2, the collision is over. The impulse is over, and now you have these two particles that are separating in the EN direction. Recall, we dealt with the E1 direction, the tangential direction, earlier in the last part where we applied linear momentum. That stays the same. So now we have a separation speed in the EN direction. And so you can see now that this coefficient of restitution can vary. And if your separation speed is equivalent to, your separation speed, which is the numerator, is equivalent to the approach speed, then what we have is a perfectly elastic collision. And that tells us that no energy has been taken out of the system during the collision. So that means that our kinetic energy before is the same as our kinetic after because of this separation speed being the same as the approach speed. Now, if energy is taken out of this system by heat during the collision, then the separation speed, we've already said, can never be higher than the approach speed. The approach speed must always be higher than the separation speed, and so that means some energy has been absorbed in the system, and so that gives us a coefficient of restitution of less than 1. So if it's between 0 and 1, then we have a partially elastic collision or just an elastic collision. And we're able to model those changes in speed of each particle simply by knowing the coefficient of restitution. Now, what dictates the coefficient of restitution, we know through experimentation, are the materials themselves. Because if you choose particular materials in your design, or if you're analyzing collisions between two different materials, they're going to have a different coefficient of restitution in between them. Now, last, we have when our coefficient of restitution is equal to 0, that means that our separation speed, the only way that can occur is that if the separation speed is equal to 0. Now, this is called a perfectly inelastic collision. We also call this a plastic collision. The other word that we've been using is a sticky collision. And this means that, and it doesn't mean that all the energy is absorbed in the system, because if it's an oblique collision, or if there's speed, things stick together as we've seen before and then they continue to move, there's still energy in the system, but this plastic collision just means that they're sticking together. Now, I mentioned earlier, and I'll drive home this point now, is that whenever you have a perfectly inelastic collision, even though theoretically our model should fit this, it doesn't, because we're violating an assumption that we made, which is that there's no friction between the objects. And so for a perfectly plastic collision, or perfectly inelastic collision as we call it, there has to be friction in between the objects, and there's a small example in the book in which that if you work through this process, you end up not getting the correct tangential speed. So if it is a sticky collision, don't use this process. Go back to conserving the total linear momentum of your system. All right, let's work an example and try to gain some insight on how momentum is related to energy changes in this system, and how we can apply these four equations that we have, or the equations that we've developed based on the conservation of linear momentum and then also this coefficient of restitution. So here we're going to solve this system in which we're giving the velocity of each particle. So we've got mass q, or particle q, and we've got an inertial velocity at time 1 of 6 in the E1 direction, which is defined for you. And then we have -4 meters per second, and that's in the negative E1 direction for our particle, this should be particle P. And then the mass of Q is 8 kilograms, and the mass of P is 10 kilograms. So the first thing that we'll apply is our conservation of linear momentum. Now this is a one-dimensional problem. It's nice and simple. We're only going to be dealing with the interaction along the line of impact. Remember, along the plane of contact or the tangential direction, there is no energy absorbed. It's a strict conservation of linear momentum, and then you can just keep those speeds the same. So the only thing that we really solve for in these problems is along the line of impact. So let's address that directly. So applying conservation of linear momentum, we get that the mass q and then vq, remember we used our v's to designate the speed along the line of impact at time 1 plus mp vp at time 1 is equal to mq vq at time 2 plus mq times vq at time 2. Let's plug in all our numbers, and so we get 8 kilograms multiplied times 6 meters per second, because it's in the positive E1 direction, and then plus 10 kilograms multiplied times -4 meters per second is equal to 8 kilograms, and then we don't know our speed of q at time 2 after the collision occurs, and then this will be plus 10 kilograms, and we don't know our speed of p at time 2. So that means we need to develop another equation that's going to help us get this, because we have one equation and two unknowns. We don't know our speed of q at time 2, nor do we know our speed of p at time 2. But we do have our expression for the coefficient of restitution, which tells us that our coefficient of restitution is equal to our separation speed on the top, so Vp at time 2 minus Vq at time 2, our separation speed, divided by our approach speed, Vq at time 1 minus Vp at time 1. And we plug in our numbers, where we get Vp at time t2, which is an unknown, minus Vq at time t2. We're solving for our separation speeds. And then in our denominator, our speed of q at time 1 is 6 meters per second, and then we're going to subtract our speed of p at time 1, which is -4 meters per second. And so when we solve these simultaneous equations for the speed of q and the speed of p, then we get Vq at time 2 is equal to 0.44 minus 5.56 E, and then we get the speed of p, V sub p, at time 2 is equal to 0.44 plus 4.44 E. And so we now have expressions for our speeds of our particles as a function of the coefficient of restitution. So let's start taking a look at how that affects the speeds given different coefficients of restitution. So let's take the first case in which the coefficient of restitution is equal to 1. And so we said that if the coefficient of restitution is equal to 1, then our separation speed is the same as our approach speed. And we get for v sub q at time vq at time 2 negative 5.1 meters per second, and then vp is 4.9 meters per second. So what's happening here in our system is that for our particle q, we initially started out with a speed of 6, or velocity of 6 in the E1 direction. And then after the collision, if it's a perfectly elastic collision, it's now moving in the negative E1 direction at negative 5.1 meters per second. And so we see here that we've lost speed, and then for our particle P, then we started out at negative 4 in the E1 direction, and then we're now leaving at 4.9 in the E1 direction. So now we've gained speed of particle P. So we've lost speed, and then we've gained speed. And we've changed directions on both of those for both of those particles. So we've lost speed and we've gained speed. We've conserved our momentum in this system. But we also said that during this, it's a perfectly elastic collision, we should have not lost any energy. And so to calculate energy for a system, and we haven't done our total energy of multiple particles yet, we'll do this next week or in an upcoming lesson, but that's TO, O being the total energy. And so let's do total energy at time 1 would be equal to, it's all kinetic energy, so it's 1/2 mq multiplied times the norm of vq with respect to O at time 1 as observed in the inertial reference frame squared plus 1/2 mp multiplied times the norm of vp with respect to O as observed in the inertial reference frame squared. And this is equal to 226.2 joules just before the collision. And so when we calculate our energy using these new speeds, negative 5.1 and then 4.9 meters per second squared, in fact we get 226.2 joules. And so we've demonstrated here that when we apply a perfectly elastic collision, we don't lose any energy, but we can see a change in speed of the particles. So where we have the value, the actual speed is 5.1, it's in the opposite direction, which is a loss of speed, and then we have 4.9, which is an increase in speed from our 4 meters per second that we began with. And as we continue down the chart, if we look at 0.75 for our coefficient of restitution, then we see that we get a negative 3.7, so we're going in the opposite direction, and we've lost even more speed with a smaller coefficient of restitution, and then we get 3.8 meters per second for our particle P, in which we've lost speed now. We started out at 4, so now we're at a loss, and then we've now lost speed, even more speed for particle Q, and then our total energy has gone even further down, so it's 126.8 joules. And then if we look at 0.5, we're now going into negative 2.33 meters per second. So we've dropped from 6 down to 2.33 on our speed, and then here we've gone from 4 down to 2.7, so we've lost even more. And you should see that reflect in the energy, in which we now have 57.3 joules. So we've dropped by a whole lot compared to our initial, which was 226.2 joules. So the energy has gone way down as we've changed our speeds, and then, or as we've changed our coefficient of restitution. And then if we do a perfectly plastic collision, then we get 0.4 meters per second, and then 0.4 meters per second, and then our total energy of our system is now 1.8 joules. So in this system, in which we started out with the mass Q of 8 kilograms moving 6 meters per second to the right, and the mass P of 10 kilograms moving 4 meters per second to the left, when we use a perfectly plastic collision, then at the end we get 0.4 meters per second to the right. So you can see that mass Q isn't bouncing and moving to the left anymore, but it's now collided together and moving to the right. These two should be the same number, but it's moving with very, very, very low energy, which is 1.8 joules. And one point that this example should reinforce as you work through more and more of these types of problems where we're applying conservation of linear momentum, and now we've introduced energy, is that you can lose energy in a system but still conserve momentum. Remember, these guys aren't necessarily the same thing, okay? They're related to each other in that they both need speed to be able to be calculated, but one of our applications here from our assumptions is that we're conserving total linear momentum. And so we're conserving total linear momentum of the system. The momentum of each particle is changing, but that whole momentum of the system is being conserved. And then how those relative speeds change with respect to each other is now giving us the energy of the system, because it's our speed that our speed that is affected by this collision. And so the energy, which we're using kinetic energy, potential energy doesn't apply here, but the energy in this system is being decreased due to this collision. And that's only going to happen if our coefficient of restitution is between 0 and 1, in which we have energy loss. And then, of course, we see here that if our coefficient of restitution is 1, then all of our energy is also conserved in the system. All right, that does it, and I'll see you in class.